Hello everyone. We've been talking about quantum cryptography and in general in the last few videos, and we have also talked about quantum key distribution, why we need a key, and the key will be distributed via a quantum channel. Okay, although the messages will be sent via classical communication public channel, but that will be encrypted, and that encryption key will be shared via a quantum channel. That is what we talked about in the last video. All right, so we will talk about a protocol where we can now we will forget about classical channel, and we will only focus on the quantum key distribution part via a quantum channel. And we will talk about BB84 quantum key distribution protocol, and it will take us a couple of videos to actually understand the protocol itself, but we will start in the idealized case today where there is no eavesdropper. Okay, I'll explain this a little bit more once I go through the video. Okay, and the bottom line is it is impossible, okay, I repeat, it is impossible for any eavesdropper according to the laws of physics to crack this key. All right, and this is the power of quantum key distribution, and this is the power of this protocol. All right, so let's start. Let's define a few quantum states. As we said in the last video that we would need four we will need 4 quantum bits, which will be, and where will be non-orthogonal pairs. All right, so we will define 4 states, and I'm giving them some name with some numbers, and you will understand why do we need these numbers. So there will be a psi 0 0, there will be a psi 1 0, there will be a psi 0 1, and there will be a psi 1 1. Okay, and the first state is nothing but the 0 state. Okay, second one is nothing but the 1 state. The third one is nothing but the plus state, so they are already non-orthogonal, and which is nothing but 1 by square root of 2 0 plus 1. Similarly, the last one would be the minus state, which is 1 by square root of 2 0 minus 1. Okay, so now there are a couple of things to notice. Is that let me use a different color. I have 2 bases here, right? This one is in a computational basis, comp basis, and this pair is in a diagonal basis, diag basis. Okay, and secondly, the thing to notice here, whenever the second bit here is 0, it is in the computational basis. Whenever the second bit is 1, this is in the diagonal basis. All right, so if I send a state and I say to someone that I send the number 0 and say that this is the basis encoding, then he can definitely say that this is in the computational basis. What I mean by that is that, let's say I send you psi 0 0, and I say that the basis encoding is 0, then you obviously know that this is the computational basis. Now if you do a measurement in the computational basis, you will definitely get the 0 state. All right, but if you do a measurement at a diagonal basis, there is no guarantee what will you get. You can either get plus or you can get minus. All right, so this is the idea, that the second bit is encoding the information about the basis on which you're going to measure. All right, and the first bit is encoding the message. It's like 0 or 1. Okay, so this is the idea. The second bit in these names, okay, are the basis encoding, and the first bit is actually the message. All right, So now how will the protocol work? So there is at least 5 steps in this protocol. We will talk about the first 3 in this video, and we will talk about it the rest of the steps and more generalization in the upcoming ones. All right, so in this video we will talk about how they distribute the key between Alice and Bob. All right, but we will not talk about any kind of eavesdropping in this video. We will just try to understand what's going on between Alice and Bob, and let's assume that there is no noise in the quantum channel and there is no eavesdropping. All right, so there's no one hampering here. This is only a now for now. We will just assume that we are trying to share a key. All right, and how can we save it from attacks, and how is it impossible to crack for an eavesdropper? We will check it in the next video. So now we will just try to understand how they're distributing. Okay, so let's assume that there is no noise. Assumption is that there is no noise and there is no eavesdropper. Okay, so and now let's see how does it go. Okay, so let's talk about step 1. So Alice wants to send the message to Bob. Okay, so how will she do that? So what Alice does is that Alice generates 2 random strings, and let's give them some name, X and Y. Okay, random strings of length m. That means, let's say this is the string x1, x2 up till xm. Okay, and similarly this y string is y1, y2 up till ym. Okay, so what I'm trying to do here, that let's say that, so okay, I was saying here that the second bit is the information about the basis and the first bit is the message. So as I said at the beginning of the video, that we want to share a key. So this is not the message that we were talking about that will be shared via the classical channel. This is the message. By the message I mean the key. Okay, so the first bit in this naming is actually a bit in your key. Okay, and the second bit is information about the basis. All right, so this is what will contain the information about the key, and this will contain the information about the basis. How? So Alice will generate states like this: psi x1 y1, psi x2 y2 up till psi xm ym. So she will create m quantum states, and let's say x1 is okay, let's use a different color. Let's say x1 is 1 and y1 is 0. Then the first state created would be psi 10, and which is nothing but this one state. Okay, so this is nothing but this one state. The second one can be similarly calculated, okay, depending on the randomly generated string, capital X and capital Y. All right, so this is what is created by Alice by some random generation of strings, and she will send it to Bob. Send these quantum states to Bob. All right, m quantum states or m qubits. All right, so these will be sent to Bob. Now step 1 is done. I hope this is clear to you what Alice is doing here. Okay, So now step 2. Okay, so please remember that we are assuming that there is no noise in the quantum channel and there is no eavesdropping. So that means that Bob will get all these qubits without any disturbance. All right, so what does Bob do? What Bob does is that he generates a random string capital Y prime. Okay, so what is that? Which is nothing but Y1 prime, Y2 prime, and it is of the same length m. So Alice and Bob will know about the value of m. Okay, so this is a randomly generated string by Bob which has no relation with Alice's capital Y or capital X. Now what Bob gets is m qubits, right? So he will get psi x1 y1, psi x2 y2 up till psi xm ym. Okay, so Alice has sent these qubits and Bob has received it. All right, now what if you remember that these y's were actually defining the basis, correct? And these x's were actually the key. So what Bob does is that Bob performs a measurement in the y1 prime basis. Okay, so if he performs a measurement in the y1 prime basis, he would get some value, either 0 or 1 or a plus or a minus. According to that, he can calculate x1 prime. Okay, so if he has calculated x1 prime, similarly he can calculate, he can do some measurement on the second qubit with the basis y2 prime, and he would get the second bit x2 prime. Similarly, for all of them, he can calculate ym prime and he will get xm prime. All right, so now Alice, after performing m measurements on m qubits in either 0 1 basis or plus minus basis, what he gets is another string x, which is x1 prime, x2 prime up till xm prime. Okay, now there is a thing to notice here, is that if y1 prime is equal to y1, then obviously x1 prime is equal to x1, correct? Because if their choice of basis is the same, and as these are eigenstates of that basis, these are the basis elements themselves. So if I send this psi 0 0 and I choose to measure in the 0 1 basis, then I will definitely get 0, right? And then my a value of x will be 0. So that is what I'm trying to say, is that if the choice of basis matches, then their x's also match. Okay, and if y1 prime is not equal to and it goes for all. So I can say that if this is I, and this is I, then x prime I is equal to xi, and this I can run from 1 to m. But if yi prime is not equal to yi, then there is no guarantee. I mean, there is no correlation between xi and xi prime. You cannot say anything about it. All right, so that is step 2. So what you can see is that whenever they have randomly chosen it, but whenever they have chosen the same basis for the same bit, then they have got the same x. Okay, so now step 3. So in step 3, what Alice and Bob will do is that they will share y and y prime. These are classical bit strings, so they can share it in the classical channel via the public classical channel. Okay, so what is happening here? Okay, let me just write it properly. Via. So what is happening here? They are sharing the information about their basis, but there is no information about the key x itself. All right, so they just shared y and y prime. So what they can do is that they can compare y and y prime. Whenever yi is equal to yi prime, so this is a small y, so this means a particular bit in the capital Y bit string. All right, so whenever yi is equal to yi prime, then they will keep that xi. Okay, and if yj is not equal to yj prime, then they will discard xj. Okay, or xj prime. If it is done by Bob, then he will keep xi prime and xj prime. All right, so you can see that if they have discarded those bits, whatever that is left, let's call that x twiddle and x twiddle prime. Okay, this is with Bob and this is with Alice. The beautiful thing is these two are equal. By twiddle, I mean that you had this bit string of up till xm, you have discarded some bits, and this is a bit string of length shorter. It can be on average be m by 2, but it can be a little bit less or more. But the idea is they have a shorter key length, but it is secret because they never shared any information about this message via the classical public channel. And if you just see the bit strings y as an eavesdropper, you will have no idea about what x was. Okay, so this is how they have shared a key, a classical key, and no one else knows about it. Okay, so this is the basic idea in the idealistic case. And now what can happen is that there can be an eavesdropper in the quantum channel. All right, and if there is an eavesdropper in the quantum channel, what can we do about that? We will talk about it in the next video. But I hope that it is clear to you how they actually got the key which is equal, and there is no chance of a eavesdropper to find it out if he has access to the public channel, because they just never shared it. All right, so please try to understand it. If you don't understand it, try to use an example. Like you can use like x1101, like a 5-bit thing, and try to calculate and assume some y prime, and then try to calculate all the bits and try to see it by yourself. Okay, I hope it is clear to you, and if it is not, please go through the video again or try to work out an example by yourself, then I'm pretty sure it will be clear to you. All right, thank you so much.